Today we will be discussing the eighth program, that is to develop a menu-driven program to animate a flag using the Bezier curve algorithm. Basically, if you can see here, we need to make use of the Bezier curves in order to generate a flag, and also it's a menu-driven program. Let us start our discussion of the program main function. So let me just scroll down to the main function. Here, if we look at the main, most of the functions are very familiar to us, like the glut init, which is used for the initialization, the display mode, which displays or takes in the arguments in the form of RGBA and single, which is the buffers, the color buffer and the display buffer. Next, we have the size of the window, the position. Next set of instructions, we have create window, which is assigned to a variable window. Then now let us come to the function create menu. Basically, it's a user defined function. So the moment we say create menu, the control goes to create menu function. So let us see what we have in this create menu function. Here we first create the menu using glut create menu. Once the menu is created, we need to add the items into the list. So here, in order to add the items into the list, we make use of glut add menu entry. And whatever is the item that you want in the list, give the name of the item, followed by a numerical value, which on pressing that value will generate that and will activate that item in the menu for you. Next, I have a menu now. For example, if this is my menu, in this menu, let us say I have one draw a flag. Inside this, I want something else. So this is a sub menu. If you want a sub menu, then we add saying that add sub menu. So here we have this instruction add sub menu, which will go under clear. That means first I'm creating a menu inside which I'm saying draw a flag. Again, I'm creating a menu within which I have clear. Then within clear, I have a submenu called as draw. Then followed by one more item, that is here. Next, I have quit. And then comes the attach menu for us. What actually is this attach menu? That is, you're trying to indicate on the click of which button the menu should operate. Here we have chosen the right button. Yes. Continuing further, if we look at this glut create menu, we call one more function called as menu. Let us move to that function menu. What do we have in this menu? Here we compare if the input, that is num, is equal to 0. If so, then we say destroy the window. That is, if you can see here, if the input is 0, we say quit. Hence we are saying destroy the window. After the destruction of the window, you just say exit. Otherwise, that means if the value that you have entered is not equal to 0, then assign it into a variable called as value, and then we call the function glut post redisplay, which makes the current window as needing to be redisplayed again and again. So that is the purpose of this post redisplay. That means with new set of values, or when you make a change, it redisplays that window with the new set of values for us. Now what happens after this execution? That is, we initially were in our main function. From here, with the call of this create menu, the control was transferred to this function. in this function we had one more invoking of function called as the menu. We went there and performed the task. Once the task is done, the control comes back to the main function. In this main function, we have the color buffer bit. Here we have this clear color wherein you are setting some values of the color. Next, you are invoking a function called as display through this display func. So now let me move to this display function. Here in this display function, you have the color buffer bit, which we all know what is the purpose of. Next, if you remember in the menu, whatever value we had assigned it to a variable called as value. So here we are saying if the value is equal to 1, then we say post redisplay, which we said that which makes the current window as needing to be redisplayed. Otherwise, if the value is equal to 2, we say push matrix. We are hearing this for the first time. What is the purpose of this push matrix? It saves the current coordinate values of the system into the stack. Similarly, here we have something called as the pop matrix. After all our work is done, it can remove the values. So I'll say pop matrix restores the prior coordinate values of the system. So that is the purpose of your push matrix and pop matrix. Now, if our value is equal to 2, where is this value coming from? If you can see, I have 0, 1, 2. If it's equal to 0, we have said destroy. If apart from that, if it's any number, it is assigned to value, and that in the display function, we are trying to work it out. We're saying if the value is equal to 1, then invoke the function post redisplay. Otherwise, if it is equal to 2, first we are pushing some values into the matrix, which is nothing but the current coordinate values of the system into the stack. And then we say color 3D, which displays some color values for us, or which takes in some color value, which is the red color for us initially. And then we have the display function, which in turn is invoking one more function called as the display func. So let us go to this function, which is the display func for us. So just let me scroll up. I see this display func here. Starting from the display func, what do we have? Here we have taken two variables. I'll say I have taken n control points, which is equal to 4, and n Bezier curve points, which is equal to 20. Now we are wondering what exactly is this. Suppose that we want a curve like this. Let me draw a curve like this, something which is very similar to our flag. Let's say I have 4 control points. The points are first one here, second control point is here, let's say the third control point is here, and this is my fourth control point. Yeah, this becomes my starting control point and this the end control point, and altogether I have defined 4 control points. So totally how many control points? 4. I'm taking it as 4 here. Yes. Next, these are the 4 major control points. How do I actually get this line here in between the control points? Basically, we know that it's a collection of pixels. How many pixels all together will generate this curve for us? We are saying that is equal to 20 for us. So put together here, I have 20 small points in between which will generate this curve in the shape of the flag for us. Yeah. Next, we have theta, which we have initialized to 0. Basically, which is used for the animation purpose. We will see where that theta is used when we come to the animation part. Next, after that, we have looked at the curve here and said that the total number of control points is 4. So let us see how exactly, or what are those 4 control points exactly. In order to define that 4 control points, here you need a space basically, that is WCPT3D is a structure, and then control points of 4. What is this? And where is this? Let me just scroll it up to the beginning of the program. If you can see, type def struct of WC PT3D, which is nothing but the word coordinate point 3D, which has the values x, y, and z. Meaning, whenever we take any coordinate, it is with respect to x, y, z values. Now let me come back here. We are defining 4 control points. How have we taken these values for this 4 control points? If you can see, I've taken 20 and 100. Let us say this is 20 and 100. So this becomes 20, 100. Observe the next point. On the x-axis, it is moving towards your right direction, the value increases, and y, it is little higher than the previous control point. Hence, I take this as 30, 110. That is this one. The first one was 20, 100 for us. Now comes the next control point, wherein if you can see again, it is moving little further on the x-axis. On the y-axis, it is coming downwards, so the value should reduce. So I'll say 50 moving further in the x-axis and 90 coming downwards on the y-axis. The next point that we have is, so third control point is done. The next point that we have is 60 and 100. Moving further on the x-axis, and going up on the y-axis. So I'll call this as 60 and 100. So that generates the control points for us. Once we are done with this, next we define the animation part. What are we exactly doing here? That is this portion where I have all of these instructions. What exactly does it do? With respect to each control point, that is, control point of 1 means it selects 30. That means this value, not this. This is 0, 1, 2, and 3. So here we are taking, when I say control point of 1, it is selecting 30. Because I'm saying dot x here. Similarly, control point of 1 dot y, it selects 110. Now, if you look at this, here, for this 30, we are adding some value. If you notice, we are not taking the control point of 0. I've started with 1, 2, and 3. So it takes this value, the second value, and the third set of value. Why exactly are we not taking this 0? Because this point remains fixed. If I change or if I apply little pressure, this may vary, but my begin point will always remain the same. Next, moving ahead, here, let us come to this portion. We said that to this 30, we have added some value. Here, it's not a mandate that you have to add 10 itself. You can add any value, but I have taken 10 multiplied by sine theta. In between, I'm taking theta plus 30 in order to say that I need some form of animation, which is in turn multiplied by pi and divided by 180. If I do not want this, then you can just say or ignore this. In that case, we know theta is equal to 0. So that means it will retain this original points itself if I do not take any new value of theta, and it will generate a static flag for us. Next, here we are saying at each step what should be the value of theta, such that it will cause the waving of the flag at a particular interval. Once this is done, that is my 4 control points are defined, and I have said that the flag should look like this in this way, and then I'm saying add some animation such that it waves at a particular interval. Next, once that is done, let us see what is the next instruction. We have the color buffer bit, which we know is associated with the color. I'll not go much in depth into all of these color, clear color or clear color 3F, etc., because these are something which we have very frequently discussed with respect to all the programs that we have understood so far. Next, we are taking the instruction point size of 5. What exactly is this point size here? You can see I have 4 control points. So I'm trying to say what is the size of these 4 control points. I'm saying it is 5. That value I'm pushing into the matrix. Next, once that is done, I'm saying here I'm generating a line in order to connect these points, and what should be the width of that line. That is done with the help of the width of the line, line width instruction, wherein I'm passing the argument as 5. That means the point size is also 5, line width is also 5 for us. Next, let me come here. I have color 3F where I've set in some color. It is nothing but the orange color code which I have set here. Next, if you can see, I've taken a for loop which is iterated 8 times. What exactly does this 8 iteration do? And inside the for loop, in each iteration, it executes these 2 instructions. What is that instruction which is being executed? Here, let us say the very first instruction is translate, meaning 8 times it translates by 0.8. For example, let's say this, my flag is here. Now, I want the flag orange color to be of this thick. Yeah. In order to get that thickness, I'm translating it by 0.8 each time. That is, initially it starts minus 0.8, come little downwards, again minus 0.8, 8 times until this entire orange color is generated for us. Yes. The flag shape would be something like this, and similarly, this would be something like this for us. Next, we are calling the, once the translate function is done at each step, we call the Bezier function. Let us discuss this Bezier function later, but remember it takes in the argument as control points, that is this set of points, followed by n control points, nothing but which says how many control points we have, which is equal to 4, and then we say n Bezier curve points, which is nothing but equal to 20, indicating how many intermediate points we have. Why do we need that? To say at each level, that is what it should do. So once orange color is done in the flag, my flag is not ready. Next, again, if you can see, I set the color for the white color here. If you can see, I set it for the white color, then I perform the same set of operation. That means here, first I have the orange color of the flag. Similarly, I have the white color. Next, after the white color is done, if you can see here, we have set the instruction for the green color, and the same set of instructions are performed. So again, this will give me, and this way the flag is generated for us. So I have the orange color, the white color, and the green color. Orange, white, and green color. Not sufficient. I need a pole. So in order to do that, what do we do? Even before that, if you can see here, we had pushed certain set of values. Now let us pop that values from the matrix. Once that is done, let us set a new color. This is nothing but the brown color for us. And next, I'm setting the line width equal to 5. And here, in order to generate a straight line, I'm making use of gn lines along with the begin function. And since it is a line, I know that I need at least two vertex. And here I've taken 2 vertex for it. So basically, this draws the line here, which holds the flag for us. So this is in brown color for us. Yes. So the stick is generated. So if you can see here, orange part of the flag is done, white part of the flag is done, green part of the flag is done, and also the stick is done. Next, again, we call the post redisplay in order to keep redisplaying the flag again and again, such that I do not want it to disappear from my screen. And then I have this swap buffer, which basically holds the background calculations, and we need to swap so that the calculations are rendered onto the screen. That means whatever calculations you are performing here is being done at the back end and is saved in this buffer. So when I call this buffer, all those calculations are rendered onto our screen. Yes. Now, from here, where do we go? If you can see, in between, I had a function called as Bezier. So let us move to that function Bezier. What exactly are we doing in this Bezier? This Bezier, if you can see, calls two more functions, that is the compute Bezier, and the other one is binomial or bino. These are the two functions that it calls. Remember, Bezier function in turn calls two functions. One is binomial, the other one is the compute Bezier point. Means we still have two more functions to visit. Let us start with the first instruction of the Bezier. And we remember what are the arguments that was passed here? Three arguments. One is the four control points, the count, and the intermediate. So here, this Bezier function, here it receives all the four control points, the count 4 and the count 20, which are the intermediate points. Now let us begin from the first instruction, where I have Bezier curve point, which is a empty argument which is passed to the structure. Next, I have U defined here, then we have C and K. These are the arguments that we have. Yeah. Next, let us come to this instruction where we have C is equal to new, a new operator which generates an array of type int whose size is 4. How do I say size is 4? N control points, that is total number of control points here for us. So whose value is equal to 4. So I'll say creates an array of size 4 for us. Next, if you can see, we are calling this function bino with the arguments n control points minus 1 and C. What is this n control, or why this n control points minus 1? I know that is equal to 3. In fact, even before you analyze this program, I suggest you watch my video on the Bezier curves, such that it will help you understand the concept of what Bezier curves is, and then follow this program exactly. Basically, when I say I have a Bezier curve of n control points, the degree is equal to 3. I repeat, if I have a Bezier curve of n control points, the degree is equal to 3. Why? Because the start point is common at all given points of time. So that means I need to compute only 3 values. Hence we say the degree is equal to 3. So here we are passing the degree and this C here, which are the control points for us. Now, let us come to this bino. Where is that function? Here. Yeah, it takes that arguments which you have passed 3 and the index to the array. Here in turn, we have taken two variables K and J. Now, in order to understand this, let me say or write two equations for you. The first equation that I'll write is BEZ Kn, I'll say, of U is equal to Cnk into U power k into 1 minus U to the power k minus 1. What is the Cnk? I'll say Cnk is equal to n factorial by k factorial into n minus k whole factorial. Even before this, let me write one more equation for you, which is the general equation. I'll write it as P of U is equal to summation K equals to 0 to N Pk Bez Kn of U, where U is a value between 0 and 1. What exactly are these? Basically, for any Bezier curve, P of U is the position vector, which is a summation of k is equal to 0 to n pk, the exact position Bez Kn of U, which is the blending function. That means I have a control point and the next control point, and what are the values here in between which joins these two control points. This becomes the blending functions for us, and that blending function is given as Bez of U, Kn of U equals Cnk into Uk, I mean U power k into 1 minus U to the power of, this is sorry, n minus k. So to the power of n minus k. Yeah. And here, what is the C of nk? It is nothing but n factorial divided by k factorial of n minus k whole factorial. These are some equations which we all should know in relation to the Bezier curve. So here, we had deviated from here while we were trying to understand what exactly is this binomial function, which is nothing but the computation of the binomial coefficients for us. Now here I have 4 control points, let's say 1, 2, 3, 4. Let's say this is placed at 1, 3, 2, 3 and 3, 3. These are the values. This is static for us. It does not change. So I'll say this is at 0, 3. Yeah. So now what I'm trying to say here is, I'm trying to take an example and say how exactly the values are computed for us. Let me take this first k loop where we say k is equal to 0, k less than or equal to n, k plus plus. If I take this 1, 3, this is not needed to be computed. Here in this case, my value of n is equal to 3, k is equal to 1. How did I write this? If you can see here, C of nk. In this case, n is equal to 3, k is equal to 1. Here, I'm taking C of k. That means initially for 0, C of 0 is equal to 1. That is, if I take this equation here, this becomes, sorry, here I've taken Bezier of, this is Bezier of 1, 3. So this becomes k equals 3, n equals 1. So this, if I substitute, you will get 1 factorial by 3 factorial into n is 1 minus 3 whole factorial. Okay. So here we have taken C of 0 is equal to 1. Next, after that, I'm taking a J loop wherein, if you can see, I'll say J is equal to N, J greater than or equal to K. The K value is 3 for us. That means starting from the value of N, which is nothing but 1 for us, it goes up till K plus 1. Sorry. I think something went wrong here. Let me just check this out. Binom of, I'm taking 1, 3 for you. So 1, 3 will be k is equal to 1. Sorry for this disturbance. I'll say k is equal to 1 and n is equal to 3. So this becomes 3 factorial into 1 factorial, 3 minus 1 factorial. So this is 3 factorial by 1 factorial into 3 minus 1 factorial. Yeah. Now, I think it should work fine for us. So, j value, what is the value of n for us? N will be equal to 3. Why? Because we have taken here. The degree is, that may, I mean, somewhere here we discussed for control points, if it is equal to 4, then the degree is equal to 3. And that itself we have passed here. So, the value of n is equal to 3. So, I'm saying starting from 3, go up to k plus 1. And at each step, decrement it. What are we trying to exactly say in this first iteration? We are saying keep multiplying until it reaches this value such that it generates this 3 factorial. That means initially I need 3 factorial into 2 factorial into 1 factorial. So that is what, or sorry, 3 into 2 into 1. So that is what 3 factorial is 3 into 2 into 1. So that is what we are trying to say here. Similarly, in the next loop, if you can see, what I'm trying to do is starting from n minus k until I reach to keeping on decrementing, I will compute 1 factorial divided by 3 minus 1 whole factorial. So that computation is done here for us. So basically, this performs the computation of the binomial coefficients. Once that is done, now let us come to the compute Bezier point. In this compute Bezier point, okay, even before I go to that, let us check here our blending function. Our blending function, if you can see, it is consisting 3 components, C of nk, uk, and 1 minus u to the power n minus k. So here, if you look at this, we have done this computation of C, N, K. We are left out with the computation of u to the power k and 1 minus u to the power n minus k. Now let us come to the part from where we had deviated. Where is that? It is here. So here I had taken the deviation invoking the binomial coefficient computation. So here, if you can see, we have computed this portion. Hopefully it is fine to you. Next, where are we? We are here at this stage. After that, if you can see, we have used line strip, and then what exactly are we doing here? That is, we know we need 20 points in between, that is these points. If you remember, these 20 points which we had called the blending functions in order to generate this curve for us. For that, we will use a loop here. If you can see, I'm saying starting from 0, go up to n Bezier points, that is 20, 0 to 20. So at each step, it computes 0 of 20, 1 of 20, 2 of 20, until it reaches 20 of 20 and it is assigned to u. Next, after that, we are computing the Bezier point, which takes the argument as u, that is nothing but at each instance what value you have computed by saying 0 of 20 and to 20 of 20. Then we have this pointer here, which is a pointer to the empty structure. If you remember, we had computed, we had assigned an empty structure here, a pointer to that, n control points, which is 4, the 4 actual control points, and C, which is this array for us. Okay, from here, our control moves to the function compute Bezier points. Here it accepts if we are sending in 4 values, 1, 2, 3, 4, 5 values, naturally it accepts 1, 2, 3, 4 and 5 values. Yeah. In this, first we initialize the degree, that is done here, which is assigned in the variable n. Next, I take one more function, variable called as Bezier blend function. Yes. Here basically we have discussed, if you remember, every coordinate that we write is collection of x, y and z. So here also we are saying each point that I write, that is here, each point that I write, I need the value of x, y, and z for that point. Initially, what is it equal to? It is equal to 0. That's what we are saying. X, y, and z is equal to 0. Yes, because we have taken an empty function. Next, we run this loop 3 times. Yeah, because that is the degree which we have defined. Now let us see what we are doing here. We know that each pk, that is this each pk is represented as, I'll say, xk, yk, and zk. I said x, y, and z in general, but this is how it goes for us. And each xk is represented as x of u is equal to summation k equals to 0 to n x bar k bez kn of u. Similarly, y of u is equal to summation of k is equal to 0 to n yk bez kn of u. And then we have z of u, which is equal to summation of k equals to 0 to n zk bez kn of u. Got my point? So here every point is represented as x, y, and z, and that x, y, and z is defined like this for us. So here we write the blending function. What is the blending function? Cnk uk, I mean u power k 1 minus u to the power n minus k. Ck power of, I mean u power k 1 minus u to the power of n minus k. Then we are writing this. X is equal to xk plus the Bezier blending function yk plus this function, sorry, into this function zk into this function. Yes. So that computes the values, which in turn will give me the value of this. Basically, by taking all of this, we get the control points xk, yk, zk. Now, once this is computed, let us come back from where we had deviated. That is, if I'm right, I had come from here. Next, I'm taking Bezier curve of x and y. Here, I've computed the values x, y, and z. But for me, what is essential is x and y. So I take all the values of x and y. How many times? 20 times. So first it takes 0 of 20. That value is passed here as u with empty these points, and then that value is stored here, and the new value of x and y is computed and which is plotted. So that happens 20 times, and that 20 times a call is made here which computes the new values of x, y, and z, which we call as the blending function. Yes. Next, once that is done, we are saying delete c. Why exactly is this delete c? Here, if you can look at this, we have made use of a new operator, and we know that new operator dynamically allocates the memory which needs to be deleted. Hence, delete of C. Now, from where did we actually deviate? We deviated from our main function. If you remember, from our main function, I called the display. Display, where is display for us? Here. Display in turn called display function. So here we have this display function. Display function in turn called Bezier. We have Bezier here. Bezier in turn called binomial and compute Bezier. So we computed the binomial, that is this part, and that is here ck, which is nothing but c of nk, which is the binomial coefficient of the Bezier curve at each position. So we have computed that, and then followed by the blending function at each position. So totally we have visited all the functions in a sequence. Now coming back to our main program, if you look at this, we are left out with the reshape function. Let me come to my reshape function. Where is that? Reshape function. Basically, it defines the new height and width whenever you make any changes to the size of the window. I'm saying adjust it in such a way, making use of the GL projections. The image is adjusted to the new window that is resized. And then we have my init. I'll not go in depth again, which is just the setting of the viewport and the ortho 2D along with the projection color, etc. for us. And lastly, we have the main loop, which is the callback function for us. So I think pretty much we have finished the program here. Now let us see how do we execute it. If I come here, if you can see, I have taken the same code which we just discussed. Let me run this for us. So if I run this, you can see the output screen being generated. Initially, I see this. I don't see the flag. The reason is it's a menu driven program. See, I have this menu clear, draw, quit. Remember, we had one menu, under that 3 items, clear, draw and quit. Under this draw, we had a sub menu, which is draw a flag. So I'll say draw the flag. It has drawn the flag. Now I want it at the front end. So I'll say, so if you can see here, I have this flag which keeps waving. That is what is the animation that we have written. And you remember we had written 8 iterations in order to generate this portion where I drew it for you, and then the white portion, green portion, animation part, and then I have the stick. And if you can see, when it is curved here, 4 control points, 1, 2, 3, 4. That way we have generated the flag. Similarly, I can say quit. So that exits the screen for us, wherein we have written the exit function, if you can recall. So this is our animated flag making use of the Bezier function. Again, I recommend you watch the video on Bezier curves in order to understand this program completely. I've just given a walk of the code and the different computations that is performed in order to generate the flag. For better understanding, please visit that and then come back to this program so you will understand in a better way, or you'll have a clear-cut idea on what exactly is the different function, or what exactly is a blending function, what is the degree, what exactly I mean by PK, PU, etc. Thank you for watching the video.